Hello everyone, welcome to Linear Model with me, Sarini Abdullah. So, for this session, we will learn about correlation, particularly about the formulation of the correlation, some examples of correlation, and then we will look further at the correlation for nonlinear functions, and then later on we will find the relation between the correlation coefficient and regression coefficient. So here we have the formulas for the coefficient of correlation, or in complete saying is the person moment coefficient of correlation, linear correlation. So on the right hand side, we have that rho equals covariance of x and y divided by the square root of variance of x multiplied by the square root of variance of y. And then this formula is what put in more detail in the second line. That is the expected value of x minus its mean and y minus its means, and then the standard deviation for each x and y. On the right hand side, we have kind of like similar formula, but instead of mu x, in here we have x bar, and instead of mu y, that is the expected value or the mean of y, in here we have the y bar. And on the denominator, instead of the standard deviation, here we have the square root of the difference between the sum squared of difference between the x bar with each data point and y bar with each data point. They are different, but they look similar. Yeah, actually they measure the same thing. But what is the difference? So let's say here we have the population in which we measure x and y. So the row in here on the left side is that the formulation for the correlation for population data. However, as we already learned in previous videos, that it's really hard to get population data in some applications. What we can do is to get sample data and we do our calculation, our analysis based on that sample data. The same with the coefficient of correlation. So if we take sample from this population, then the one that's given by the formula on this right side is that the formula for the correlation between x and y for the sample data. As we can see from this formulation, this is between x and y, and then we can just interchange the terms in the formula. Y comes first, x comes later, and also here is that x minus mu x, y minus mu y, or in here is of order 1. So here we can see implicitly from this formula that the correlation measures the strength of linear relationship between x and y. Now we look at some of the examples. Here are the visualization of scatter plot between x and y for some hypothetical data. For here on the left side, we see that this kind of like a linear, although it's not really strong, and as x increases, y also increases. So in here, if we do the calculation, we get it. This result is based on R package. So we get the calculated correlation is 0.5647972, and it shows a weak positive correlation. On the other hand, on the right hand side, we see that the slope of the line is negative, and we got the correlation is minus 0.5956954. So we see that there is a correlation between x and y. However, because the dots, the points are scattered quite wide, not concentrated really on the line, we say that these are kind of like weak correlation. When the line has a positive slope, then it is a positive correlation, and on the opposite, it's a negative correlation when the line has a negative slope. Here's another example. Now we see the line are more concentrated along the line, although not all of the points are exactly on the line, but the points are more concentrated. So we can say that it's kind of like getting stronger, the correlation. And then we are given that the correlation between x and y for the left plot is 0.9340768, a strong positive correlation. And then on here is even stronger, and we can see that the correlation is 0.9964891, and is negative, showing that increased x associated with the decrease in y values. Now this is a perfect correlation. We say it is a perfect correlation if all the points x, y, they all are on the line. So here we have a perfect positive correlation for a line that has a positive slope, and here on the left we have a perfect negative correlation. Now we have the question, because we need correlation is as a preliminary analysis before we move on to the regression analysis. And then we learned that in linear model, the term linear in linear model doesn't have to only accommodate a linear relationship between the predictor variable, that is x, and the response variable, that is y. So it's just reasonable to ask whether the linear correlation only measures the linear function. Here we see from our example. Let's see, we have scatter plot like this. And then if we are to fit this plot using using a linear line, a straight line here, we see that the correlation is almost zero. And it just makes sense because, for small x, for large x, the value of y is just scattered. They have low values and high values as well, no matter what the value of x. So it just makes sense that to say the correlation between x and y is really low and is implied by this result. However, if we look at the line, at the data on the right plot, it's clearly seen that the points are forming a quadratic trend. But if we are to calculate the linear correlation for this data, and then we fit a linear or a straight line to this data represented by this red line, then we can see that almost all of the points are outside the line, scattered away from the line. And then the linear correlation is given by minus 0.01556437. It's such a really low correlation. If we think of correlation as how strong the relationship between two variables, we might think that this is not a good result. Yes, it is not a good result because it says that the correlation is really low, but visually we can see that there is a really strong relationship between x and y. But So, how to get an agreement between those two statements? Let's say that we calculate the correlation between x squared and y. Why we put the x squared? Because from our mathematical background, we know that this is a quadratic, so we need to incorporate a quadratic term. That's why if we try to calculate the correlation, the linear correlation between x squared and y, then we will have a 0.995 1013, which is a really strong correlation. And then if we put the quadratic line over here, the quadratic equation, then it will fit properly to the data. So in this case, we can see that the linear correlation can also measure other kind of relationship between variables, but in order to identify that relationship, we need to do the visualization to help us look at what functions that really need to link between these two variables. This is another example that we see that um, if we put a linear correlation between just x and y, then we will have kind of like low correlation. But if we apply our mathematical background on forms of the functions, we know that this is an exponential function. So if we try to find a linear correlation between exponential value of x and y, or the logarithm of y and x, then we will have a perfect correlation in here. So again, even for a linear function, we can still measure the strength of the relationship between those two variables. Doesn't have to be a linear function. It can be an exponential function as long as we put in the right or the correct functional form in the place of x and y. So here we learn from this video that the coefficient of correlation measures the strength of linear relationship between two variables, but it does not necessarily only applicable to linear functions.